All right, so let's get started with week 8 of interactive live sessions for the course on fundamentals of convective heat transfer. It's being offered by NPTEL and instructed by Professor Amaresh Dalal from the Department of Mechanical Engineering at IIT Guwahati. My name is Debjit. I'm a PhD scholar at IIT Madras, and like every other week, we shall be solving some problems together. Now, without further delay, we'll dive into it. This week, our discussion has been on uh, natural convection and the flows and heat transfer associated with it. And Grashof number is one such non-dimensional number that becomes very important in the context of natural convection. So what is this Grashof number a measure of? So it's basically a ratio of two kinds of forces. Which are they? Is it option A, inertia force to viscous force? Is it option B, buoyancy force to viscous force? Is it option C, inertia force to surface tension force? Or is it option D, buoyancy force to inertia force? Let us quickly take a look at the answer. It is actually the buoyancy force to viscous force. So that's what our Grashof number is. So basically, if we look at the formula, it boils down to something like this, into some h cube divided by mu squared. Now this on the numerator is a representation of the buoyancy force, and the viscosity squared on the denominator is a measure of the viscous force. So ratio of these two forces uh, is represented by the Grashof number. It's not exactly equal to the ratio of the two forces, but a representation of that ratio. So which is why this becomes important. If let's say a Grashof number is very, very low, that means that the buoyancy force is not as much. In that case, natural convection won't play much of a significant role. Whereas in the other case, where Grashof number is very, very high, then we can conclusively say that the uh, physical phenomena going on is dominated by natural convection, and that is dominated by and driven by these buoyancy forces. All right. So let's move on. Let's move on to question number two. We look at another important non-dimensional number now, known as the Rayleigh number, often represented like this, Ra suffix some h, or in this case L. So what is it given by? Is it given by option A, beta delta T uh, L cube G by nu square? Is it beta delta T L cube G by nu alpha? Is it nu alpha over beta delta T L cube into G? Or is it option D, beta delta T L to the power 4G divided by nu into alpha? And here all the variables represent their usual meanings. So I'll just quickly go through them. Beta is the coefficient of bulk expansion. Delta T is the temperature difference. L is the characteristic length scale. G is the acceleration due to gravity. Nu is the momentum diffusivity, or also known as the uh, coefficient of kinematic viscosity, and alpha is the thermal diffusivity of the material. Okay, so let's take a look at the solution. It's actually option B, this one. So Grashof number and Rayleigh number are usually related like this. So Grashof number is actually equal to the Rayleigh number multiplied by the Prandtl number. So our Rayleigh number should be Grashof number divided by the Prandtl number. So if we write down whatever we know that Grashof number is delta T L cube into G by mu square divided by Prandtl number. Sorry. Uh, Sorry, it should be multiplied by Prandtl number. So Rayleigh number would be Grashof number into Prandtl number. So I should be multiplying this with the Prandtl number, and as a result, I'll cancel out one nu, and alpha will get multiplied. So this is what our Rayleigh number would be, and that matches with option B. Okay, and these are the relations between the Grashof number, Rayleigh number, and Prandtl number. So the Rayleigh number is a product of the Grashof number and Prandtl number. All right, so let's move on. We'll now move on to question number 3, which is here the Prandtl number becomes important. So the question is asking us that for high Prandtl number fluids, where the Prandtl number is much, much greater than 1, and natural convection over a vertical isothermal wall. So these are all important keywords. So I have a vertical wall, which is isothermal at the same temperature, and there's some natural convection going on there. So in that case, a boundary layer would develop, and I'll have obviously uh, a velocity or a hydrodynamic boundary layer, and the thickness of it would be given by, let's say, delta, sorry, be given by delta, and at the same time, I will have a thermal boundary layer develop as well, where let's say the temperature difference will go something like this, or rather the temperature itself might go something like this. It's we're doing this for a hot wall, so yeah. So this is what the temperature or the thermal boundary layer would look like, and this would be given by the thermal boundary layer thickness delta T. So what should be the relationship between delta and delta T? Is it option A, delta would be much, much greater than delta T? Is it option B, delta is much, much less than delta T? Or is it option C, the delta should be proportional to or of the same order of delta T? Here the important hint is that the Prandtl number is much, much greater than 1. So Prandtl number is the ratio of the momentum diffusivity to the thermal diffusivity, and this being much much greater than 1 means that the momentum diffusivity is much much greater than the thermal diffusivity. So what happens in this case is that the thermal boundary layer is thin, so it follows a inverse law. So the thermal boundary layer, sorry, not an inverse law. So that's why delta would also be greater than delta t. It comes from here. Since momentum diffuses, since momentum diffusivity is high, the momentum diffuses to a greater distance as well. As a result, this delta would be much, much greater than delta t. So what happens is that if I, let's say, have a vertical wall like this, the thermal boundary layer would be pretty thin. So on this line, let's say the temperature comes down and becomes equal over here, more or less equal. That's where the thermal boundary layer ends. But uh, there will definitely be, a high velocity here, but there will be a velocity outside as well. And sorry, let me draw this correctly. There will be a high velocity here, and the velocity would carry on to higher depths. So let's say somewhere here. I'm really drawing this in a poor scale. Let me draw this in a better way. Ah, so- yeah. So it will take some time for the velocity to become zero. And so see, the thermal boundary layer only is this much thick, given by delta t, but the velocity boundary layer extends beyond it, so given by delta. So delta would be much, much greater than delta t. Right? Okay. So let's take a look at the solution. It is indeed that delta is much, much greater than delta t. Now take a look at the other case where the Prandtl number is low. In that case, what happens? And we stick to the same case of a natural convection over a vertical isothermal wall. So in this case, what happens? Is it option A, delta much, much greater than delta t? Or is it that delta is much, much less than delta t? Or is it option C, that delta and delta t are of the same order? So in the previous question, we saw that for high Prandtl number, delta is much, much greater than delta t. So it might be natural to expect that delta should be much, much less than delta t for very low Prandtl number fluids, but it's not the case. Actually, the correct answer is option C, that delta is proportional to delta t. And let's take a look at the reason behind that. So once again, if we have a wall like this, let's draw the temperature profile first. So, okay, so the Prandtl number is much, much less than 1. As a result, alpha is much, much greater than nu. So we can expect that the thermal boundary layer is pretty thick. So let's say we start from here and then we take some time before we can reach the temperature. So this is roughly where the thermal boundary layer ends. This being delta T. Now, it's not that the velocity boundary layer or the thermal boundary layer is simply smaller just because our uh, nu is much, much small or Prandtl number is much, much small. Thing is, in this whole region from within the thermal boundary layer, there is a difference in the densities because of heating. And as a result, the entire fluid within that boundary layer has a motivation to move. As a result, it obtains a velocity, and delta is actually, uh, or sorry, the delta is actually of the same order as delta t because this entire region has some finite velocity. Sorry. So if I try to draw the velocity boundary layer, it will go something like this. So there will be a non-zero velocity until this point, and then it will become zero. So this distance where it becomes zero, this is delta. And delta t are of the same order and very close to each other in magnitude as well. Now, what it means is that if we consider another smaller region where you know, this is also known as delta V. This delta V is the region where the inertia forces, or sorry, the viscous forces balance out the buoyancy forces. As you can see, there's a huge velocity gradient here. As a result, viscous forces are high. Whereas in this region, like above delta V and beyond, here the temperature gradients are much smoother. And in that region, it's the inertia forces which dominate and balance out the buoyancy forces. The buoyancy forces are anyway there wherever there is temperature difference causing the density difference and as a result, buoyancy force. So delta V in this case might be much, much smaller than delta T as a result of Prandtl number being very small, but delta doesn't really change. That is of the same order as delta T. So you have to wrap your heads around this particular physics of the problem. So until and unless you do that, you might get misguided and simply select this option B where delta much less than delta T would seem like the natural conclusion going from the reasoning of the previous question. Okay. All right. So if things are clear, we will keep moving on. We'll move on to question number 5 now, which is asking us about another important non-dimensional number known as the business number, or sometimes given by BO by H. Not to be confused with bond number, which is also represented by BO at times. So in terms of Rayleigh number and Prandtl number, what should it be? Should it be a product of Rayleigh number and Prandtl number? Should it be the ratio of Rayleigh number and Prandtl number? Or is it option C, Rayleigh number powers 1/4? Or should it be option D, Rayleigh number multiplied by Prandtl number powers 1/4? The product being 1/4 to the power 1/4. All right, so let's take a look at the solution. It's actually option A, the product of Rayleigh number and Prandtl number. We earlier saw that the ratio of Rayleigh number and Prandtl number is the Grashof number, and their product is the business number. This becomes important in many cases. And what should be the mathematical expression of it? So I'll write down Rayleigh numbers times Prandtl number. Rayleigh number is basically beta delta T L cube G divided by nu into alpha, and our Prandtl number is nothing but nu over alpha. So this nu cancels out, and what we are left with is beta delta T L cube G over alpha squared. This is what the business number represents. All right, so moving on. We'll move on to question number 6. Once again, another non-dimensional number known as the Richardson number. And there is some very direct physical significance of this Richardson number, which we will look at once we solve this problem. And this question is asking us the definition of a Richardson number. Is it option A, the product of Grashof and Prandtl? Is it option B, the ratio of Grashof to the square of Reynolds? Is it option C, simply the ratio of Grashof number and Reynolds number? Or is it option D, the ratio of Rayleigh number and Prandtl number? Richardson number, often given by Ri with a suffix. All right, so let's take a look at the solution. It's actually option B, the ratio of Grashof number to Reynolds number. So this number actually shows up when you non-dimensionalize the momentum equation for the boundary layer equation that comes up for natural convection, where you will get the coefficient of the viscous term as 1 over Reynolds number, and Grashof number by Reynolds number squared becomes the coefficient of the buoyancy term. So this actually represents the actual importance of the buoyancy term with respect to the others. So Richardson number given by Grashof number by Reynolds number squared. So Since this represents the importance of buoyancy term, so if Richardson number is much, much greater than 1, we can say that the flow is entirely, or the heat transfer is entirely through natural convection. If the Richardson number is much, much less than 1, we can say conclusively that there is no forced convection mode of heat transfer at all, and it's entirely forced convection. And where Richardson number is close to 1, we can say that both natural and forced are important. Right. So it really tells us the importance of which mode of convection is more dominant in a particular situation. That's why this is very important. Okay, so we'll move on. Now the question refers to some scaling laws. So for natural convection on a vertical plate with uniform heat flux, what does delta T scale as? Does it and delta T is the thermal boundary layer thickness. So does it scale as y power 1/4, and y is the streamwise direction in this? So if I have a vertical plate like this is my y coordinate, this is my x coordinate. So if a boundary layer develops like this, sorry, this is the thermal boundary layer, delta T. So how does delta T scale as this direction y? Does it scale as y powers 1/4? Does it scale as y power 1/5? Y power minus 1/4 or y power minus 1/5? And remember, this case is related to uniform heat flux, where Q is fixed and not Ty. That would be the isothermal case or the uniform wall temperature case, but that's not it. We are worried about for the uniform heat flux case. So we saw in the lectures that scaling laws can dictate that in the uniform heat flux case, delta T goes as y powers 1/5. So in the so for the uniform temperature case, we can find out how delta T scales with y and Rayleigh number, and within Rayleigh number, if we simply replace the temperature difference with the temperature difference we will get in case there is uniform heat flux, we can easily show that the scaling changes from 1/4 to 1/5 in the case of uniform heat flux. Okay, so we should remember this, and then moving on to the last question of today's session. So in case you have a cylinder like this and you want to cool it, so this could be anything. This could be like a can of some beverage or beer that we have, and we need to cool it very quickly. So by placing obviously by placing it inside a refrigerator with cold ambient air. But what do you think? In which orientation would it cool faster? If we keep it up straight, in case of case one vertically, or in case two, if we keep it laying down horizontally. In which case would it cool down quicker? So let's not get into math here. If you think physically, what does your intuition tell you? Which one should it, which one seems like it should cool faster? If you're in a hurry in what, and given the option, you have the option to keep it either way, which one would you, reflexively choose? So if you think you'll place it in a horizontal way, then you're correct. And in fact, you can show this mathematically as well. So I got this solution from the internet. I'll just, you know, zoom in and show you the results. So these are pertaining to some particular numbers. So let's say this person says that, standard can dimensions. So this is related to a can of a cold drink or beer. So the standard can dimensions are 4.8 inches in length and 2.6 inches in diameter. And the typical refrigerator temperature is 40 degrees Fahrenheit. And initial temperature you can take something like 75 to 100 degrees Fahrenheit, which is, the outside temperature, the ambient temperature. And uh, assuming nothing else, uh, it would finally show that it would be 3% faster if you put it in the horizontal orientation. Now, this 3% would depend on the exact dimensions and everything, but it is faster. You can show it. So this is how the solution goes. Initially, we pick the average temperature and consider the properties of air for that temperature. We get beta and we can calculate the Rayleigh number pertaining to it. And the Nusselt number for a vertical cylinder is given by this particular uh, formula. And once you plug in the numbers of the Rayleigh number, you will get the Nusselt number. From the Nusselt number, you can find out the rate of convective heat transfer. And similarly, so this is for the horizontal case. Sorry, I must have said vertical in between. That's not the case. This is H represents horizontal. And similarly, you can find things out for the vertical case as well. We find out the Rayleigh number first. And one thing is the Rayleigh numbers would change because of the characteristic lengths of natural convection changes. So if you keep in the horizontal direction, it's the diameter that is the characteristic length scale over which the boundary layers develop. But if you keep it in a vertical manner, then the length of the can becomes the characteristic length scale because that is the length over which the boundary layer develops. So that is another way in which the Rayleigh number becomes different for the two cases. And the another source of difference is the Nusselt number itself, which relates to the Rayleigh number in a very different way. So for a vertical cylinder, this is how the uh, Nusselt number depends on the Rayleigh number, and you can find out the Nusselt number is 24 in this case, and you can find out uh, the coefficient of heat transfer in this case as well. So if you compare the two H's, you can see that the H for horizontal is 5.18 something, and for the vertical case, it is 5.05, close to that. So now if we take the difference and divide it by the vertical case as the standard, we will see that there is roughly a 3% increase in the heat transfer rate. So if you keep it horizontally, it will cool much faster. Okay, so that's all from my side. Thank you. Let's meet again next week.